Accurate, up-to-date sidewalk data is essential for building accessible and inclusive pedestrian infrastructure. Yet current approaches to data collection are often costly, fragmented, and difficult to scale. Today, we introduce iOSPointMapper, a mobile application that enables real-time, privacy-conscious sidewalk mapping on the ground, using recent-generation iPhones and iPads. This system leverages on-device semantic segmentation, LiDAR-based depth estimation, and fused GPS EMU data to detect and localize sidewalk-relevant features, like traffic signs, traffic lights, and utility poles. To ensure transparency and improve data quality, iOSPointMapper includes a user-guided annotation interface that allows mappers to validate the system's output before submission. Collected data is anonymized and transmitted to the Transportation Data Exchange Initiative, TDEI, where it integrates seamlessly with broader multimodal transportation datasets. Detailed evaluations of the system's feature detection and spatial mapping performance reveal its potential for enhancing pedestrian mapping. Together, these capabilities offer a scalable, user-centered approach to closing critical data gaps in pedestrian infrastructure. Let's begin with the problem. Sidewalks form a critical component of the public right-of-way, enabling pedestrians to move safely through urban and suburban environments. Yet unlike roadways, which benefit from substantial investment in maintenance and monitoring, sidewalks often suffer from neglect, both in infrastructure and in data. This neglect disproportionately affects individuals who rely on sidewalks as their primary means of travel: people with disabilities, older adults, and those without access to personal vehicles. The lack of high-quality, up-to-date sidewalk data hinders local governments, transit agencies, and nonprofit organizations from making informed decisions about maintenance, compliance with accessibility regulations like the ADA, emergency response planning, and equitable investment. Despite growing demand for accessible, multimodal transportation networks, there remains a significant gap in scalable, standardized systems for assessing and monitoring sidewalk environments. A centralized, reliable mechanism to collect and manage this data would benefit a wide array of stakeholders. Government agencies could use such systems to prioritize infrastructure investments, enforce ADA compliance, and improve emergency response. Private companies, like delivery services and sidewalk robotics firms, could enhance operational efficiency by understanding traversability in pedestrian environments. Advocacy groups could leverage data-driven insights to push for equitable funding. And communities would gain safer, more walkable neighborhoods and increased mobility. One major initiative addressing this challenge is the Transportation Data Exchange Initiative, TDEI, led by the Taskar Center for Accessible Technology and funded by the U.S. Department of Transportation under the ITS-4 U.S. Deployment Program. TDEI enables the integration and sharing of data on pedestrian pathways, transit services, and dynamic mobility networks through a common platform. It also supports machine learning tools like Profit, which uses aerial imagery and rasterized road network topologies to detect sidewalk features. But aerial methods have limitations: occlusions from trees and buildings, variable resolution, and difficulty capturing fine-grained details in complex urban settings. In many cases, a ground-based approach is necessary to provide high-fidelity, real-time assessment of pedestrian infrastructure. To address this gap within the TDEI framework, we present iOSPointMapper, a mobile application designed for ground-level mapping of sidewalk environments. It runs on recent-generation iPhones and iPads, equipped with high-resolution cameras and LiDAR sensors. The app uses real-time, on-device convolutional neural networks to perform semantic segmentation and feature detection, minimizing latency while preserving user privacy. Only anonymized geometric and semantic data, such as the location and width of a sidewalk, is sent to a central repository. No raw images or personally identifiable information are transmitted. Recognizing the importance of human oversight in AI-assisted systems, iOSPointMapper includes a built-in annotation interface that lets users vet the system's output before submission. This increases data reliability, fosters transparency, and empowers users to participate in scalable mapping efforts without relinquishing control. Once validated, the data is uploaded to a specified workspace within the TDEI platform, enabling seamless integration with existing systems and facilitating data-driven transportation planning. With this work, we aim to establish a scalable, privacy-conscious, and user-centered approach to sidewalk data collection, helping close critical data gaps in pedestrian infrastructure by enabling community-informed, ground-level assessments at scale. So how does it work? At its core, iOSPointMapper uses a real-time computer vision pipeline to detect and classify sidewalk-relevant features. The system begins with semantic segmentation, assigning each pixel in an RGB image to a specific class. The model outputs a dense segmentation mask, which is then stabilized across frames and converted into discrete features suitable for localization. For this task, we use CNET-EV2, a lightweight convolutional neural network designed for real-time performance on edge devices. It employs a dual-branch architecture, a detail branch for high-resolution spatial features, and a semantic branch for contextual understanding. This design is optimized for mobile deployment, working seamlessly with Apple's CoreML framework. We trained the model on 5 key sidewalk-relevant classes: sidewalk, building, traffic sign, traffic light, and pole, all of which appear frequently and with high visual variability across environments. These features are seminally important for understanding sidewalk infrastructure and are often underrepresented in vehicular-centric datasets. To bridge the gap between automotive and pedestrian perspectives, we built a custom training corpus using a two-stage approach. First, we curated a subset of the Mapillary Vistas dataset, prioritizing images with strong sidewalk presence, resulting in 4,300 pre-training images. Then, we collected RGBD video data across Seattle and Bellevue, using LiDAR-enabled iPhones mounted on chest straps to emulate a pedestrian viewpoint. From these videos, we extracted still frames and manually annotated them to highlight sidewalk features under varied conditions, resulting in 200 training and 50 validation images. In the training pipeline, we first pre-trained by CNETEV2 on the curated Mapillary subset, then fine-tuned it on our custom dataset. To preserve low-level feature extraction, we froze the detail branch while training the semantic branch and segmentation head. This strategy improved the model's ability to localize small but critical points of interest, like poles and signage, while maintaining spatial accuracy across diverse sidewalk geometries. To enhance segmentation stability, iOSPointMapper leverages the temporal continuity of real-time video. When a user captures a frame, several preceding frames are processed as well. These are aligned using homography transformation, and their segmentation masks are merged via a per-pixel majority vote. The resulting mask is then passed through contour detection to extract discrete object instances. This allows the system to convert dense pixel-level predictions into discrete, map-ready features, ideal for localization and mapping. The user interface is designed for intuitive engagement. On the setup view, users select which feature classes they want to map. Then in the camera view, they see a live camera feed overlaid with real-time segmentation masks. When satisfied, they capture a frame, which triggers the annotation view, a user-guided vetting interface. Here, users can validate all instances at once with options like agree, discard, or missing. For finer control, they can expand a dropdown to inspect individual instances and reject or accept them selectively. This flexible workflow places the user directly in control of the output, ensuring transparency and trust. Now, how do we turn these detected features into geospatial data? At the moment of capture, iOSPointMapper synchronously records a dense depth map from LiDAR, camera intrinsics, camera pose, position and orientation, and device GPS coordinates. Using ARKit, the system backprojects the centroid of each segmented object into 3D space, transforms it to world coordinates, and then translates it into geographic coordinates via spherical projection. This pipeline ensures orientation-invariant localization, meaning users can hold their device freely while mapping. All geolocation computations happen entirely on-device, eliminating the need to transmit any personally identifiable information. For Sidewalk specifically, iOSPointMapper performs additional geometric estimation. To focus on the segment the user is currently traversing, the app analyzes confidence maps from the model to define a region of interest, ROI. Pixels labeled as sidewalk, but falling outside this ROI are excluded. Within the ROI, the system identifies the largest valid trapezoidal region that approximates the portion of the sidewalk directly in front of the user. This is done using a top-down bounded traversal that evaluates horizontal lines from top to bottom to determine upper and lower bounds. The centroid of this trapezoid becomes the localization point. The geometric bounds of the trapezoid also enable physical measurements, such as sidewalk width, by projecting the top and bottom edges into geospatial coordinates and averaging their lengths. These metrics are crucial for quantifying sidewalk accessibility in terms of compliance with ADA guidelines. Once validated, the data is transmitted to the TDEI platform via TDEI workspaces, a shared interface for managing multimodal transportation datasets. Users log in through the app's login view, authenticating access to a designated workspace. Upon login, a new change set is opened, a logical grouping of edits by a single contributor. Each accepted feature instance is sent as a distinct node containing structured metadata, GPS coordinates, change set ID, user ID, and attributes like sidewalk width. Importantly, iOSPointMapper executes the entire Open Sidewalks feature extraction pipeline on device. All segmentation, object identification, and geometry construction happen locally. Only the resulting sparse traversal abstraction, georeferenced sidewalk nodes and associated attributes, is transmitted. Raw imagery is discarded after inference. This design eliminates the need to upload high-bandwidth image or video streams to a cloud service, removing a major transmission bottleneck. It ensures predictable upload requirements in low connectivity areas and reduces latency between capture and availability for downstream applications. By transmitting only essential map primitives, rather than raw sensor data, the app supports scalable field deployment and strong privacy protections for passersby and adjacent properties. Let's look at the results. We evaluated the system on an iPhone 16 Pro, equipped with a LiDAR scanner, triple-lens camera system, GPS, and EMO. All data was captured via Apple's ARKit and core location APIs. In the feature detection phase, we benchmarked 3 by CNETEV2 variants. By CNETEV2 City, trained only on cityscapes, a vehicular-centric dataset. By CNETEV2 PED, pre-trained on Coco stuff, then fine-tuned on our custom pedestrian dataset. By CNETEV2 iOS, pre-trained on a curated subset of mapillary vistas, then fine-tuned on our custom dataset. This is the model deployed in the app. On a held-out validation split of our annotated pedestrian view dataset, by CNET-EV2i OS outperformed both baselines across all metrics. For the Sidewalk class, it achieved a mean IOU of 0.7782, a substantial improvement over by CNET-EV2 cities 0.0881. Visual comparisons show that by CNET-EV2 city often misclassifies sidewalks as roads, while by CNET-EV2i OS correctly identifies them as sidewalk surfaces. For traffic signs, traffic lights, and poles, performance improved progressively with training alignment to the pedestrian viewpoint. While traffic lights and poles remain challenging due to occlusion and clutter, by CNET-EV2i OS demonstrates strong generalization across all classes. This confirms that pedestrian-centric pre-training and annotation are critical for accurate feature detection in sidewalk environments. Next, we conducted field tests in Seattle, Bellevue, and Redmond, each with a 3-kilometer stretch of sidewalk. A single annotator used iOSPointMapper to perform continuous ground-level mapping. We evaluated localization accuracy and sidewalk width estimation. Results show that large grounded features like buildings and sidewalks are localized with low error, mean error under 1 meter, RMSE under 1.2 meters. Smaller or more distant objects, especially traffic lights and poles, exhibit higher variance, largely due to limitations in segmentation accuracy and LiDAR depth estimation beyond 5 meters. Occlusion and urban clutter further complicate detection. Sidewalk width estimation remains within acceptable bounds for accessibility-focused use cases. Errors are amplified in scenes with complex ground geometry or reduced depth visibility. But when isolating objects within 5 meters of the user, both localization and measurement accuracy improve markedly, often below 0.5 meters RMSE. These results underscore the promise and current limitations of on-device mapping in uncontrolled urban environments. Future work will explore photogrammetry-based reconstruction to improve depth assessment for distant or occluded objects. Finally, we visualize the end-to-end workflow. In TDEI workspaces, captured features appear as labeled point nodes, such as poles, traffic signs, and sidewalks. Continuous sidewalk segments are rendered as connected line geometries, supporting intuitive inspection of both discrete objects and structural elements. This demonstrates successful integration from on-device recognition to centralized, standards-compliant data storage. What does this mean for inclusive mobility? iOSPointMapper, as part of TDEI, represents a significant step forward in addressing long-standing data gaps in sidewalk infrastructure assessment. By combining real-time, on-device AI with user validation, it enables a participatory mapping model that empowers municipal staff, advocacy groups, and community members to contribute using off-the-shelf devices. This democratizes data collection, supports equity-focused investment, and enables precise accessibility assessments, all while protecting user privacy. Looking ahead, we're planning several enhancements. We'll refine the segmentation model to improve robustness under poor lighting, occlusion, and atypical geometries. We're also expanding the feature set to include curb ramps, critical for ADA compliance. For localization, we're exploring photogrammetry and dead reckoning techniques to improve accuracy for small or distant objects. Future versions may also estimate sidewalk slope, cross slope, and surface integrity, key attributes for accessibility. We're also working on integrating with municipal asset inventories, allowing agencies to overlay existing GIS data for in-field validation and redundancy reduction. And ultimately, we aim to integrate iOSPointMapper data with open ecosystems like OpenStreetMap and regional GIS platforms, enhancing interoperability and civic engagement. As these datasets grow and standardization improves, this work contributes to a more open, transparent, and equitable transportation data commons, one that doesn't just build better sidewalks, but fosters more inclusive cities. In conclusion, iOSPointMapper is a mobile application designed to support scalable, privacy-conscious, and user-centered sidewalk data collection on the ground. Through real-time on-device processing, human-in-the-loop validation, and seamless integration with TDEI, it bridges critical data gaps while respecting user agency and data privacy. As development continues, expanding its sidewalk scene understanding capabilities and interoperability with open data ecosystems will position iOSPointMapper as a key enabler of inclusive, data-driven mobility solutions. This is not just about mapping sidewalks. It's about building a future where every person, regardless of ability, age, or access to a car, can move safely and independently through the cities they call home.